Addiction is not merely an individual problem, it is a phenomenon with far-reaching social consequences. Healthcare expenditures rise, family relationships deteriorate, and indirect risks such as traffic accidents increase. Moreover, addiction is not limited to substances. Social media, gaming, and gambling addiction all operate through different channels, yet share a common logic. Short-term rewards generate disproportionately large long-term costs. Intervention strategies are therefore crucial. However, a key question remains. Which intervention is most effective, for whom, and at what point in time? Should prevention be prioritized, treatment capacity expanded, or policies targeting the social environment strengthened? These questions cannot be answered through good intentions alone. They require a more measurable perspective. This is precisely where mathematical modeling becomes relevant. An analogy helps clarify its role. Intelligence functions like a powerful engine, whereas mathematical modeling acts as the steering wheel and the map. The engine provides momentum, but without a map it is impossible to know where one is heading, which route is being taken, or how safely progress is being made. In some studies, addiction is approached not as a static label, but as a dynamic process unfolding over time. In models examining alcohol use, the population is divided into groups such as individuals at risk, moderate users, those entering treatment, and those who have quit. Individuals move between these groups at specific rates. The aim is to identify where the process accelerates, where it slows, and where intervention may have the greatest impact. It is important to emphasize that a mathematical model is a simplification, not a replica of reality. Yet when constructed carefully, it offers something valuable, a more realistic way of addressing the question, where should we intervene first? Within such models, we can test scenarios such as how increased social influence affects risk, whether improved access to treatment reduces heavy consumption, or how quitting rates change when treatment effectiveness improves. These are not definitive conclusions. They are scenario-based evaluations. Still, this is exactly what policy design requires, an informed sense of direction regarding the likely consequences of specific actions. A similar logic applies to studies on alcohol consumption among individuals with diabetes. In a medically vulnerable group, identifying which factors most strongly influence consumption patterns allows for more targeted interventions, instead of uniform solutions applied to everyone. Finally, although alcohol and social media addiction differ, they raise comparable societal questions. What increases the likelihood of initiation, and where the critical threshold for intervention lies? Mathematical modeling helps make them measurable. Mathematics does not trivialize addiction. It helps manage its complexity by reminding us that time and resources are limited, and that effective responses must be guided by data and reasoning, rather than intuition alone.